The fuel system on the ISM represents the most advanced fuel control system available today. This system uses electronics to precisely control fuel metering and injection timing functions. This computer-based system improves engine performance, optimizes fuel economy, and reduces exhaust emissions. The ECM processes inputs from sensors and switches to provide precise engine fueling and injection timing. The ECM cooling plate contains an internal fuel tube that circulates the fuel through the cooler. Excess heat generated by the ECM is transferred from the ECM into the fuel. This prevents the ECM from overheating. Isolators on the cooling plate help to prevent the transfer of heat from the engine to the ECM. The positive displacement gear-driven fuel pump is driven by the accessory drive. The pump incorporates a pressure regulator set at approximately 150 psi. This provides a relatively constant pressure to the injectors through fuel tubing and drillings in the cylinder head. Excess fuel flow from the pressure regulator is returned to the inlet side of the fuel pump. The pump assembly includes the fuel pump, shutoff valve, and fuel filter mount. The ISM utilizes the new FleetGuard Stratapore fuel water separator filter. This filter is 98.7% efficient at removing particles 10 microns in size or larger. The filter features finer filtration, improved water removal, increased contaminant capacity, and increased service life. This filter was specifically designed to offer extra protection to the fuel system. The suction tube in the center of the fuel filter provides quicker engine starts. This tube causes the fuel pump to draw fuel from a lower level in the filter. This prevents any air in the top of the fuel filter from entering the system at startup. The filter contains a high-capacity 10-micron filter media, which progressively filters debris, offering better protection than traditional media. The 5-layer Stratapore filter is 98.7% efficient at removing 10-micron particles with nearly twice the dirt-holding capacity compared to typical cellulose synthetic filter media. The increased contaminant capacity provides performance previously obtained only with primary-secondary filter systems. The filter removes 85% of all of the water in the fuel. The improved water removal provides a higher level of engine protection. The water in fuel or whiff sensor installed in the bottom of the filter senses when the water level in the filter reaches the contacts on the sensor. When the water in the bottom of the filter reaches this level, an electrical flow path is created across the contacts. This signal to the ECM indicates a high water level at the sensor. The ECM then lights the maintenance lamp to alert the driver that the filter must be drained. This provides real-time feedback to the operator to drain the fuel filter. The new ISM injector provides increased fuel flow to meet the higher power and lower emission demands of the engine. Fuel flows from the fuel tank to the fuel filter. The filter may be either pump-mounted or remote-mounted. In either position, the filter removes water and debris from the fuel before sending the fuel onto the fuel pump. The fuel pump is a positive displacement gear-type pump. Fuel is pulled into the fuel pump inlet by the rotating gears. The gears pressurize the fuel and direct it through internal passages past the fuel pressure regulator. The fuel pressure regulator in the fuel pump is set to approximately 150 psi. At the regulator, excess fuel is bypassed to maintain the desired pressure in the fuel system. Fuel to the engine flows through the filter screen and onto the shutoff valve. When the valve is de-energized, it stops the flow of fuel out of the fuel pump. When the valve is energized by the signal from the ECM, the solenoid opens the passage out of the fuel pump. From the fuel pump, fuel travels to the ECM cooling plate behind the ECM. The fuel traveling through the cooling plate cools the ECM electronic circuits and reduces excessive heat buildup in the ECM. From the cooling plate, fuel flows through the supply line to the cylinder head. An internal fuel drilling in the cylinder head supplies fuel to each of the injectors. The injector includes the top-stop shim, injector control valve, spring guide, timing chamber, bias spring, metering plunger, pressure relief valve, closed nozzle subassembly with its cup, needle valve and return spring, metering check valve, metering spill port, fuel drain passage, fuel supply passage, timing plunger, bottom stop shim, return spring, and the top stop assembly. Full-time double pulse injection is being introduced on the ISM engine. At the start of metering, the metering plunger and the timing plunger are at the lower limits of their travel. The injector control valve is closed. As the camshaft rotates, the timing plunger return spring forces the timing plunger upward. Fuel flows past the metering check ball and into the metering chamber. This flow continues as long as the timing plunger is moving upward and the injector control valve is closed. Supply pressure, acting on the bottom of the metering plunger, forces it to maintain contact with the timing plunger. The ECM determines the end of this first amount of metering by signaling the injector control valve to open. Fuel at supply pressure then flows into the timing chamber, thereby stopping metering plunger travel. During this time, the bias spring ensures that the metering plunger remains stationary and does not drift upward as the timing plunger moves upward. This same force against the metering plunger results in enough fuel pressure below the plunger to keep the metering check ball seated. Then, at approximately 150 crankshaft degrees before injection, the solenoid closes again. Fuel pressure is again directed to the metering chamber. This allows an additional amount of fuel to enter the metering chamber. Opening the valve again stops the flow of fuel into the metering chamber. Reducing the delay between the time the fuel is metered into the injector and when it is injected into the cylinder allows for better control of the fuel metered into the injector and improves accelerator response. A precisely metered quantity of fuel is now trapped in the metering chamber. This determines the quantity of fuel that will be injected. By controlling when the valve opens, the ECM determines how much fuel is metered into the metering chamber. Opening the valve sooner in the cycle results in less fuel in the metering chamber, and opening the valve later allows more fuel in the chamber. This same fueling process was used on M11 engines. However, due to limitations in the ECM, double pulse injection was limited to engine speeds of 1,000 RPM and less. This system was referred to as part-time double pulse injection. With improvements in the ECM and the redesigned profile camshaft, the ISM engine is capable of full-time double pulse injection. The timing plunger continues to move upward until it reaches the end of its travel. As the plunger moves up, the timing chamber fills with fuel. As the timing plunger begins its downward travel, the injector control valve remains open. This allows fuel to flow from the timing chamber through the injector control valve to the supply passage. At the appropriate time, the ECM closes the injector control valve, trapping fuel in the timing chamber. This trapped fuel acts as a solid hydraulic link between the timing plunger and the metering plunger. The ECM controls injection timing by when it sends a signal to the control valve to close. Closing the valve sooner results in advanced timing, and closing the valve later in the cycle results in retarded timing. As a result of this hydraulic link, the metering plunger is forced to move downward with the timing plunger. Because the fuel is trapped, the downward force on the timing plunger is transferred to the metering plunger. This movement of the metering plunger increases the pressure in the metering chamber. When the pressure in the metering chamber reaches approximately 5,000 psi, the needle valve begins to be forced upward against the needle valve return spring pressure. Continued downward movement of the timing plunger and metering plunger results in a steadily increasing fuel pressure. As a result of this increasing pressure, the fuel is forced past the needle valve, through the spray holes, and into the combustion chamber. Injection continues until the spill passage of the metering plunger passes the metering spill port. The pressure in the metering chamber drops rapidly, allowing the needle valve to close abruptly. This action results in a positive end of injection. This prevents dribble and results in cleaner combustion. The high-pressure fuel from the metering chamber causes the pressure relief valve pop-off. This reduces the effects of the high-pressure spike that occurs at the time of the metering spill. The relief valve passage connects to the fuel drain line. Immediately after the metering spill port is opened, the upper edge of the metering plunger passes the timing spill port. This allows the fuel in the timing chamber to be spilled into the fuel drain as the timing plunger completes its downward movement. This completes the injection cycle. By varying the amount of time the injector control valve remains open and remains closed, the ECM is able to maintain precise and independent control of metering and timing values. The fuel from the timing chamber and the pressure relief valve exits the injector and flows through the internal fuel return rail in the cylinder head. This fuel returns to the fuel tank through the fuel drain return.